I uh, I just felt like doing this checklist of some of the important concepts in SWK, and I think let's start with moments. We're going to do two versions, the scalar and the vector format. So let's start with the vector format. With the vector format, say we have a body that is subjected to a force F that is passing through point A and a point, P somewhere there. So if the question says find the moment about point P, it must be the position vector from the point to the force cross the force. It's always the position vector from the point to the line of action of the force. Any point on the line of action of the force. So, one thing that we must note is that with the cross product, with this statement that we have written, is that MP will be perpendicular to PA, and also MP will be perpendicular to F. So the moment is perpendicular to both the vectors in the cross product. The order matters when you do your cross product. MP cannot be F cross PA. That cannot happen, right? So it's something that you must note. The order does matter. Other thing that we can do is the magnitude version. So with the magnitude version, say we have a body that is subjected to a force F at a point at a distance d from the origin. So meaning if we were to find MO, moment about point O, it would be F times d, right? With normally we usually show that counterclockwise is positive. So this is something that you must note. And here you see it doesn't matter because it's just simple multiplication, so that doesn't matter. But with the cross product using vector notation, be careful of the order. This is the right order. Okay, let's talk about maybe finding moment about a line. So moment about a line. Well, moment about a line, let's say we have a body, same in that case, F, that passes through point A and has a point P somewhere there. And they're looking for moment about line L. I'm just going to call it line LL. So if we were to find moment about the line L, the first thing that we do is that we need to first find the moment about a point that lies on the line. So in this case, it will always be PA, because it's always from, because we're looking at it from the line, it should be from the line of action of the axis or point that is on the axis to the line of action of the force. So this will be the moment about a point on the line of, about a point that is on the line or on the axis. So what you have to do again is that, if you notice, is that now you have found moment about a point. So now you need to project this moment to the moment about the line LL. So in this case, we're going to find the dot product of UL. And if you find the dot product of the moment about a point with the unit vector UL, you're actually finding the magnitude, because here you're getting a vector and here you're getting a vector. So if I'm looking for the vector notation of it, I'll just multiply by UL again. But remember, this is the dot product here. I'm just going to say dot there so that you don't forget and you don't get it confused with that one. So let's recap on that. It should be the moment about a point that lies on the line or on the axis dot it with the unit vector of the line of the axis. If you can get it, then multiply it with the unit vector of the line if you're getting the vector notation of it. Recap on equivalent systems. So we have noticed now that if we have a force, a system that has a force Fr and a moment m, and that moment is perpendicular to Fr, the equivalent system can be written in just Fr only. And what we can note is that we first moved our Fr from point A to point P. By moving that, we had to compensate by adding a couple moment MP, and we have realized that MP is also perpendicular to Fr because of the cross product of MP being AP cross F, so Fr, so meaning that MP is perpendicular to Fr, and that M is also perpendicular to Fr. So what we did is that we took sum of the moment of the perpendicular axis equals to 0, and we realized that M perpendicular equals to minus MP due to equilibrium, meaning that our system can then be represented by that with just a force alone. Then we had a second case that we called a range. So with the range is that we started with Fr, which is a force, with a moment m that is not perpendicular to Fr. So what we did is that, okay, let's first find the component of m that is perpendicular to Fr, and that is parallel to Fr. And what we note is that because that is perpendicular, we can then simplify our system into Fr and M parallel, because if we have a system that has a force that is perpendicular to Fr, we can only have Fr. So that's the same concept that we used above. So we will be left with Fr, but M parallel will stay there because we cannot cancel it. And by having this equivalent system, we're going to call it a range, as I have said it on as a heading up there. So a range is like the moment that is parallel to, it's a force with the moment that is parallel to the force. And what we note is that this equation also plays an important role with vector notation, that m equals to m perpendicular plus m parallel, right? Meaning this, if I have m parallel and m, I can actually determine m perpendicular. How would I determine my m parallel? M parallel, remember these are vector notation, sorry. So m parallel will just be the f unit vector of Fr, since I'll have the resultant force of Fr. If I dot the unit vector with m, what I'll have is the magnitude, but if I multiply it back with UFR, the unit vector, then I'll have a vector notation, hence I've put the bar on top of that. So it is very important to always understand the theory behind this, right? So the other thing that we can talk about is equilibrium. So with equilibrium is to know that if I'm using 2D, I have 3 equations, meaning I can solve 3 unknowns, right? And those equations are some of the forces in the x, some of the forces in the y, normally, if that is my axis, and some of the moment, say about a point. So those are my 3 equations, meaning I can solve 3 unknowns. So if I'm on 3D, meaning I have 6 equations in total, meaning I can solve 6 unknowns. And those equations, I have some of the forces in the x, some of the forces in the y, some of the forces in the z, all equals to 0, and some of the moment in the x, some of the moment in the y, and some of the moment in the z, all equals to 0. Alright, so meaning I can solve 3 unknowns. If I have 6 equations and 7 unknowns, then my system will be statically indeterminate, meaning I cannot solve it without any additional information that has to do with maybe the deflection of the body or something which is not what you'll be covering in SWK. That will be covered in some of the courses as you go and continue with your engineering degree. And I'm not sure what I'm forgetting, but I feel like if you go through this, you should be fine. Oh, maybe let's talk about reaction forces again. On reaction forces, anything that prevents translation in a certain direction causes a reaction force, and anything that prevents movement in a certain, rotation in a certain direction creates a reaction moment. So that's all with reaction forces. You don't have to cram what's happening from the textbook. And there's another thing to note in your textbooks on your reaction forces, fine print in your textbook. They tell you that if the support is supported, like if the system is supported somewhere else, the couple movements that are developed in the support are actually excluded. Can you please go read on that and make sure you get it? But what it means is that if it's supported somewhere else, besides being supported with the tension, the couple moments that we usually generate in our, what do you call, in our support, maybe your general bearing, if you had moments, usually you exclude them. All right. Another thing to note, I don't know if you guys use the double arrows to represent moment or the other way around, but remember, always use the one that the lecture suggested. And I think with that, if you go through this video, you should be fine for the semester test. And all the best.